Good morning, dear students. Once again, all are welcome to the class. So here we begin with our fourth module of classical mechanics. Here we will discuss Alemberts principle and its application to many mechanical systems. Okay. Previous class, as you know, we studied about the principle of virtual work. And by making use of principle of virtual work, we solved many mechanical problems. Okay, so we could understand many dynamical systems making use of the principle and related equations. We could write, we could understand the physics involved in many mechanical systems. And this time we will study some dynamical systems. That means which are moving. Or either you are not essentially in static equilibrium, because principle of virtual work we essentially use for systems which are in static equilibrium. That means any system which experiences some forces, but the system as a whole is not moving. Okay, that was the concept in static equilibrium. There are forces, but due to the forces, system is not moving. It is not making any net effective movements. But there are certain other systems in physics, in our day-to-day life, or in the world around us. Many systems are there which are under motion due to forces. So when forces are there, there can be many forces. Applied forces may be there. There may be frictional forces, there may be constrained forces. Okay, so under such situations, when so many varieties of forces are acting on a system, we need another formalism to solve such situations or solve such moving systems. Okay, that is usually dealt with another principle that is known as Alemberts principle. Alemberts principle. Okay. Using Alemberts principle, we can solve any dynamical system which are in motion and are experienced or acted upon by many applied forces and many constrained forces. So we will see today that. Okay, and we will use the principle of Alemberts law to solve many dynamical systems. And you would like to know that it is another way of writing Newton's second law of motion. We know second law of motion tells you how the rate of change of momentum and force are related. Okay, that is basically it tells you Newton's second law. And you can, in one sense, you can say that you can know in English language we usually write sentences. You can either write in active voice or you can write in passive voice. So, if you tell in an over-exaggerated way, this is something like that. Okay, writing in two different formats. But Newton's law has its own limitation, or Newton formalism has its own limitation. But Alemberts formalism you can make use in any situations, especially when there are so many constrained forces acting on the system. Newton formalism may be a little bit too tedious. Okay, too tedious, but Alemberts formalism will be can be used more effectively in such situations. Okay, and okay, as you told already, virtual work principle you can use only when system is in static equilibrium. But most of the systems, you know, in nature are not in static equilibrium; they are in dynamic equilibrium. That means forces are acting and things are moving. Okay, so this was solved by a French mathematician known as Alemberts. Okay, so that law principle which today we will study, and he used the principle of virtual work and modified it to include dynamical systems. Okay. And you can solve many problems. Some typical examples are given here: a pendulum, it's a moving system, planets moving around the sun, is a system, moving system, dynamic system, an harmonic oscillator, a cylinder rolling down an inclined plane, a car moving along a rough surface. Okay, the last example you can see so many constraint forces are acting on it. So you will get a more generality in the solution with respect to Newton's second law. So in nutshell, the principle can be stated like this. You consider a system having n number of particles, capital N number of particles. Then you can define the principle like this. For a system containing capital N number of particles, the sum of difference of the force, okay, acting on the system and the time derivative of the momentum is 0 when projected onto any virtual displacement. So that's a statement. Okay, you write in a mathematical form, it looks like this. You are summing up n number of particles. There are Fi is the force acting on the ith particle, and you can see Pi dot. So that is actually called reverse effective force. Minus Pi dot is called reverse effective. It is a mathematical manifestation of the statement we have made at the beginning. Okay, we will explain in detail the physical essence of this equation. Okay, so don't worry about that. And this law is known in another name also called the Lagrangian Alemberts principle. And as I already mentioned, it is an alternative form of Newton's second law of motion, but has some additional advantage compared to Newton's second law. And you see the difference in Newton's law. We write force equals mass times acceleration, while in the Alemberts law we write force minus ma. So that is called, according to Alemberts language, this is called a reverse effective force. Minus ma is reverse effective force. If there are n particles, so we signify with phi mi a like that. There is only a single particle or a single body, you can write it f minus m. So that is a difference. So for generalization, we use the subscript I. That is all. And so it can be said that the object is in some sort of equilibrium. So that's the essence of D'Alembert's principle. D'Alembert's principle count any dynamical system as a system which are at instantaneous equilibrium. Okay, instantaneously at equilibrium. Okay, for that instantaneous value, we take Fi minus mi for any time instant. Here Fi is called the real force or the applied force, and minus ma is called the fictitious force or reverse effective force. In many textbooks, different terminologies are used, and we have used all the terms here. Fictitious force, in some books we will see fictitious force, in some books we will see reverse effective force, and in some other books you will see inertial force. Okay. Anyway, these are all the terms used to signify minus mia. So the physics of this equation is that instantaneously, the sum of applied force and the reverse effective force is instantaneously. Okay, that is the core concept of D'Alembert's principle. And you can solve this equation for any dynamical system. You will get equations of motion, whatever required value you can get. Acceleration, equation of motion, velocity or position with respect to time, anything you can solve for any dynamical system. We will take some examples for it. Okay. According to Newton's law, we write, you can see a little bit elaboration of the D'Alembert's principle. In Newton's law formalism, we write like this: Fi equal to my Pi dot. Pi dot indicated dp by dt, rate of change of momentum with respect to time. Okay. So we can bring back Pi dot to the left hand side. We have Fi minus Pi dot equals 0. And he say, according to the Boy equation, a moving system of particles can be considered to be in equilibrium. You can underline the word equilibrium. Under a force equal to the actual force Fi plus a reverse effective force minus V. Okay, these are different different ways to express D'Alemberts principle. Okay, previous slide also we have seen the statement and corresponding equation. This is also a statement of D'Alemberts principle. Equivalent statement. You can opt for any statement. Okay. So on writing like this, what happens? The system reduces to a static. You can say a static equilibrium system. And these keep in mind, these are for instantaneously static. Okay. It's a mathematical for procedure. Okay. So don't take it into any physical sense. That means at every instant there is an equilibrium between the applied force and the reverse effective force. That's the meaning. Every instant there is an equilibrium. Okay. And the reverse effective force also called inertial force, because it is something like a pseudo force acting on a body placed in an accelerating frame of reference. Here is a elaboration given. You have a car moving, number of people are acting upon it. So the total force on the car you can write as summation of Fy. Okay. And a value phi depends on how many number of people are applying force on the car. And there is an effective acceleration vector A. So there is a count at any time instantaneous position. And then there is a reverse effective force on the car that is taken as minus. Understand? So you assume that the dynamical system is assumed to be static for any instantaneous time by adopting the D'Alemberts formulas. Okay, and here the core idea is to convert a dynamical problem into a static problem by introducing the concept of inertial force. Okay, this is a visualization or a perception or an intuitive idea. You can explain in any one of the. Okay. So that is where the intellect of the D'Alembert comes. Okay. So by assuming that like that, you can solve many problems and you will get identical results as that of Newton's law. Here is a problem. Consider a block of mass 40 kg acted upon by a force P. Okay. There is a force here. You can see this is the force acting at a particular direction 30 degree with the horizontal, and the block is moving with acceleration 2 meter per second square, given that the coefficient of friction is mu k equal to 0.3. So find the force P. We can use the D'Alemberts principle. Okay, so this okay. So this diagram shows what are the forces acting over it, and we can take a component equation, one for x component or horizontal component and one for vertical component. Understand? So we have the diagram here. We can have an horizontal equation, we have acceleration, and corresponding to mu k there will be a reaction or a resistive force acting on it in the opposite direction to the applied force. Okay, we have an applied force given here. So the equation along the x direction you can write like this. Applied force is P. So P's cosine factor is acting along the horizontal direction, and this is the resistance component 0.3 N, and is the normal reaction that is equal to mg, and the reverse effective force is mass into acceleration. So we have the D'Alemberts equation for the horizontal component. Similarly, you can write the D'Alemberts equation for the vertical component. And on solving these two equations, you have two unknowns and two equations. Solving, we will get the value of this applied force, that is equal to 218 Newton. Okay, it's a simple problem to elaborate the idea of the D'Alemberts principle. And you may have again the question of what is the inertial force. Here is once again reminding you, inertial force, which is the force which acts in the opposite direction of the accelerating force and is equal to the product of the acceleration and the mass of the force. And why the name inertial force? It is arising from the frame of reference concept. It is known so because it is the same as the fictitious force experienced by a body placed in an accelerating frame of reference. So where we call it as fictitious force. Okay. Something like which we experience when you are in a bus and the bus happens to be suddenly accelerating. So you experience a backward thrust. So that can be that can be counted as a reverse T force for a point of argument. Okay, and now let us express the Alemberts principle in its fullest form. We can write it for any virtual displacement, the principle of virtual work for a dynamical system. You can rewrite your principle of virtual work in a new form. We have delta W equals to summation Fi minus Pa dot delta R. Okay, if you project into the virtual displacement form, and the Fi may contain both applied forces and the constrained forces, as I told you earlier. So force can be written. That means the force acting on the ith particle can be written as Fia plus Fic, where Fia is the applied force and Fic is the constrained force that may involve many forces, both frictional and other constrained forces. So first equation can be modified in this form. And as you know, constrained force do no work, so its product with the virtual displacement will be 0. So our modified equation will be like this, okay, because constrained force do no work. That's a fundamental principle for the cases which we are interested in. Such cases, constrained force do no work. So removing this term, we get a delta W equal to summation I is equal to 1 to n. 1 to n is coming because we assume that the system contains n number of particles. And maybe a system may contain 2 particles, 3 particles, 4 particles. Accordingly, the number of equations will get reduced. And this is what is called the Alemberts principle. And you can take the delta R outside, virtual displacement outside, and you can write it in a new form. So this is the final form of the Alemberts principle. And using the Alemberts principle, we can extract the dynamical equation for all moving system. We will see some demo problems and we will see how the Alemberts principle is employed to solve such systems. And here is some snippets for you, just reminding you of your previous knowledge. When a system is said to be static equilibrium, when a mechanical system is said to be static equilibrium, these are not a part of the syllabus, still it would be fine to know the idea. When all the forces acting on an object are balanced, that is, there is no resultant forces and the object is not in motion related to a frame of reference, then we call the system is in static equilibrium. Okay, an example is given. Pans of a balanced being. So if the pan is a balanced state, so then there is no motion, but still forces are acting over it. Okay. And another term is very usually coined in mechanics, that is dynamic equilibrium. When all the forces acting on an object are balanced, but the object is still moving with a constant velocity. Okay, this kind of situation may arise. Forces are acting on it, particle is moving. Okay, so moving, that is why this word dynamic coming. An example is given here. For your better understanding, an example is given here. A metal ball falling down through a viscous fluid with terminal velocity. Usually happens when a ball is thrown into a viscous liquid. Initially the ball accelerates, then finally it achieves a constant velocity and it moves throughout the rest of the time with the same constant velocity. So that is a case where dynamic equilibrium condition is possible. Okay. So many situations we have in physics, you can make use of that. Now let us try to illustrate the D'Alemberts principle with some of the standard typical problem. Here is one problem. A body is there which is moving along an inclined plane. The plane is at an angle theta with respect to the horizontal, and the surface is frictionless here. For our convenience, we have taken a simple problem. So frictionless. And you know, wherever the body is, there is an mg acting downward. Of course, this will have one component, horizontal component and one vertical component. Horizontal component is mg sin theta and vertical component is mg cos theta. Okay, and mg cos theta will constitute as normal reaction. Okay, normal reaction. And Fi. We are using the D'Alemberts principle here, Fi minus Pi dot delta Ri equal to 0. And here Fi delta Ri, because the system consists only a single particle, your I become 1. So we have mg, this is the force acting upon, applied force is mg sin theta multiplied by Watt's displacement. And you have the Pi dot here, Pi dot delta R, that will be equal to m d square R by dt square delta R. Okay. And since constraint is not doing any work because n is perpendicular to delta R, as we studied in the principle itself, you can neglect this part. So I is equal to 1 only, and this actual replacement for the particular case you can take as S. So you rewrite the above equations in terms of S. So we have mg sin theta delta S minus, okay, this is a reverse effective force, minus m d square S by dt square delta S equal to 0. So here D'Alemberts principle is written. Now you can see, identify this with D'Alemberts principle. Summation is removed because only one particle is there. Okay. So mass you can cancel. So you have g sin theta delta S minus d square S by dt square delta S equal to 0. Again delta S is not 0. So you can equate with d square S by dt square. And on integration, you get the equation of motion of the moving body, that is equal to half gt square sin theta plus some initial value, boundary value that can be computed by applying appropriate boundary conditions. Okay, so this is a formalism followed in D'Alemberts principle to solve the problem of body moving on an inclined plane without any friction. Now take another problem. Here there is a friction. Okay. Again you have an inclined plane. You have an inclined plane here, and here instead of falling, the body is moving up. It's a more realistic problem. There is a friction also. Consider a body weighing 300 Newton. Okay, not kilonewton, simply Newton. He is pushed up at a 30-degree plane by a 400 Newton force, okay, acting parallel to the plane. If the coefficient of kinetic friction is 0.2, okay, moving friction is 0.2, what is the acceleration of the body? It's a simple question. You are pushing a body, a mass of weight 300 Newton. The friction is given here, so we can find the constraint acting on it. Angle of inclination is given. And applied force is also given, external force. Very typical D'Alemberts law can be applied. So we can find the frictional force or the constraint force. Okay, this is opposite to the applied force. So mu times W cos alpha. Okay, this is acting in the other way. This is acting in the opposite way. This is a constraint force. And applying D'Alemberts principle, what we get? We have the applied force, we have a constraint force. It is opposite, not perpendicular. So we have to count it. Whereas in normal reaction, you can remove because displacement and the normal reaction are purely perpendicular to each other. So that is removed. And this is a reverse effective force. And this is the quantity which we want to compute. A. Okay. So we can insert all the values. We have a single particle, so I is equal to 1. So we have Ft, that is applied force or tangential force, minus W sin alpha. Okay, this is not because this is the opposite reaction. Minus F. Okay, and this is a frictional force, and this is a constraint force, frictional force, minus reverse effective force equal to 0. So we set the D'Alemberts equation. You can apply the values now. 400 minus 300 sin 30 minus 51.9, already we have calculated, minus mass times acceleration. On computation you will get the acceleration. Okay, so this is the formalism followed in D'Alemberts principle. Here we explain the system having friction also. Come to the third example. Here we have a pendulum. Okay, pendulum moving freely in air. So air friction is not counted. The length of the string is of value small l. Let at any time instant, let the angle of deflection be theta. It makes a substance, the string substance, an angle of theta with the vertical. So mass is acting downward. So mg, weight is acting downward, mg. So it can have two components. One is a tangential component, mg sin theta, which is the external force on this body. And there is a exactly downward component, mg cos theta. This is essentially a constraint force which makes in equilibrium with the tension acting on the string. And you can count any virtual displacement delta s at any given time instant delta s. So we can write it as L delta theta equal to delta s. No doubt, from the figure it is clear. And we have the D'Alemberts equation here, Fi minus Pi dot. Okay, so Fi into delta Ri we can write as this is the Fi. So minus mg sin theta L delta theta. Okay, this is the virtual displacement. And similarly, Pi dot, how you will write? P equal to mass times velocity. Okay, and velocity you can write as L theta dot. Okay, V equals to R omega velocity. So omega is d theta by dt. So that is what is shown here. Okay, theta dot. Theta dot is equal to d theta by dt. So if you take once again differential Pi dot, so we have ml theta double dot. Other things are same. Okay, so Pi dot is equal to ml theta double dot. So we separately calculated Fi and the Pi dot. Now we can insert inside the D'Alemberts equation. Okay, inside the D'Alemberts equation we can insert, and we will predict that the motion is periodic, motion is oscillatory, like that. Okay, so that means a prediction comes by formulation. We will predict, and let us see whether the prediction becomes true or not, whether it is an oscillatory motion or a periodic motion. So we can proceed. We have the D'Alemberts equation. Let us put these values, which values already we calculated. Okay, we have minus mg sin theta L delta theta minus ml theta double dot L delta theta. Common things we can remove. So what is left behind will be minus g sin theta minus L theta double dot equal to 0. Okay, or you can rearrange this equation. We have the theta double dot equals minus g by L sin. Okay, so this is nothing but d square theta by dt square equals to minus g by L sin. Okay, so this is a standard differential equation. You can solve it by integration. On first integration, you will get an equation of this form. So we have now the d theta by dt. Okay, with a cosine factor, and we have a constant which can be easily computed with applying boundary condition by taking time is equal to 0 and initial displacement as 0, like that. And again, once again, a differentiation is given, and if you will finally reach the okay, so we get the value of theta at any time, and this is the equation of motion of the simple body. Okay, hope the idea is clear. So this is the formalism followed in D'Alemberts principle to do a mechanical problem and write the equation of motion and calculate any requisite value of any physical parameter of that system. Okay, so hope the idea is clear to you. Formalism is clear, how D'Alemberts principle is coming and how it can be employed on different mechanical systems. Like this. You can go through many other problems given in standard textbooks. You will enjoy it. Okay, here is one problem like that. Here, two masses are attached on an inextensive string. Okay, and it is taken to a pulley. Okay, and constraints are there. You can see forces are there, applied forces are there, constraints are there. You can use the D'Alemberts principle. Okay, two masses are interconnected with an inextensive string of length L to a frictionless pulley. Prove that the acceleration A of the mass system is, okay, here the final answer is given. Acceleration of the system will be m1 minus m2 divided by m1 plus m2 times g, where g is the acceleration due to gravity. Okay, and you can also write it as d square L by dt square equals to m1 minus m2 by m1 plus m2 to g. Okay, here L is the length of the string. Okay, length of this rope. You can imagine like that. In other notations, you can take as you wish. You do this problem, you will get enough help from standard textbooks. Go through it, study it, then do the problem and submit it in due time in Google Classroom. Okay. So, with these remarks, I hope let us conclude here. Wish you all the best. Thank you.